All right, welcome. Today we're diving into something pretty wild. It's a speculative theory about the very fabric of reality, and it's called Clifford, the universe's command code. So let's just kick things off with a massive question, a real mind-bender that gets to the heart of this whole thing. What if everything you see, everything you are, from the tiniest particle to the biggest galaxy, runs on a simple, elegant two-number code?
Okay, so before we can even talk about the code itself, we got to look at the universe in a totally new way. Let's start with this idea of a universe-sized atom.
So, the big idea here is what's called the aniscopic atom. Now, this theory suggests that the universe isn't just, a bunch of empty space with atoms in it. No, it's saying the universe is one single massive atom. And here's the kicker. The laws of physics that govern it are the same at every single scale. What happens at the quantum level mirrors what happens at the cosmic level.
And this is where it kind of clicks, right? Just think about it. You've got a galaxy spinning around a supermassive black hole. How is that different, really, from an electron buzzing around the nucleus of an atom? It's the same pattern, just on a scale that's almost impossible to imagine. This idea that the rules are the same no matter the size is the absolute key to all of this.
Okay, so if we accept that the universe is this one giant atom, then you have to ask, right? How is it programmed? And that's what brings us to the math at the heart of it all, this two-number code.
And there you have it. That's them. The whole entire theory really just boils down to the tension, the push and pull between these two little numbers. You've got 0.402. Think of that as our reality, the physical hardware of space-time we can see and touch. But then you have 0.39, and that's something else. It's like an influence leaking in from other hidden dimensions. It's the cosmic glue holding our reality together.
So what does this hardware of space-time actually look like? Well, according to this theory, it's not a perfectly smooth ball. It's an icosahedron. That's a 20-sided shape. And the most important thing about it is that it's imperfect.
And why does that imperfection matter so much? Well, think about it. A perfect sphere is stable. It's balanced. Frankly, it's kind of boring. It just sits there. But an icosahedron? It has all this built-in geometric tension. It's got edges and points. And that stress, that structural push and pull, is what actually creates everything. It creates energy, force, even the flow of time itself.
All right, now brace yourself, because this is the part that might just blow your mind. The theory lays out a specific mathematical formula for how these code values translate into geometry. And when you plug in our two numbers, just look at what pops out. The number for our reality, 0.402, maps almost perfectly to pi divided by 2, the number that defines perfect 90-degree angles. And the number for that binding force, 0.39, it maps to the golden ratio, phi, the number for natural symmetry that we see everywhere from seashells to galaxies. I mean, come on, that's a jaw-dropping connection.
So, okay, we have the code, we have the geometry. But how does a bunch of abstract math actually create, us, the physical world? Let's break down how this geometry actually forges reality.
It's actually a pretty straightforward four-step process. First, you start with that geometric code we just talked about. That code creates a vibration, a quantum frequency. Then, that frequency generates the binding energy, that cosmic glue. And finally, when you trap that energy inside the geometry of space-time, boom, we perceive it as mass.
This just turns our whole idea of mass completely on its head. See, in this model, mass isn't stuff. It's not a solid thing. Mass is the vibration. It's the echo, the resonance of a quantum frequency that's been caught and trapped inside that icosahedron cage of spacetime.
Now, I know what you're thinking. This is a really cool thought experiment, but does it actually predict anything? Can it solve any real-world mysteries? Well, this is where the theory gets seriously compelling. Let's look at the cosmic answers this code might just give us. So remember our two main numbers, 0.402 and 0.39? Well, the difference between them is tiny, right? It's just 0.012. But that little gap isn't just some leftover math. In this theory, that gap is everything. It's the beat frequency of the entire universe. It's the cosmic pulse that makes everything happen. Okay, so what happens if you convert that tiny frequency into an actual energy value, something physicists can measure? Well, you get a very specific number, 6.13 kilo-electron volts, or keV. Just hang on to that number for a second. Because, get this,
For years, astronomers have been picking up this weird, unexplained X-ray signal coming from deep space, from huge galaxy clusters. They don't know what it is, but it peaks somewhere between 3.5 and 7 keV. And a lot of them think it might be the signature of dark matter. And where does our theory's prediction land? 6.13 keV, right smack in the middle of that observed signal. Coincidence? Maybe, but wow.
And it's not done yet. The theory also predicts that this exact same pattern should show up again, but at a way, way smaller energy scale. It suggests there's another resonance that could explain the bizarre, almost non-existent mass of the neutrino, predicting a value right around 0.12 electron volts.
So now, just step back and look at the pattern here. You've got the cosmic frequency related to 0.012, and you have the predicted neutrino mass related to 0.12. Do you see it? It's the same fundamental number, just shifted by a decimal point. This is that aniscopic principle we started with, in action. The same command code, apparently running the show at the biggest and smallest scales of reality.
So, where does that leave us? With a pretty staggering thought. If any of this is even remotely true, it means that reality isn't just described by math, it is math. It's a geometric program running on a simple code. And that leads to one final, huge, mind-bending question. What happens when we figure out how to write the code ourselves?